And welcome back. As we continue our cosmic journey, looking at the different life cycles of stars, we need to take a moment to kind of ask yourself, how do we know a lot of this different information, especially since stars live a long time? And to do that, we're going to need to actually look at star clusters. And this is going to be very important for how we determine star life cycles. Because again, how do we know how stars move through their evolutionary life cycle? After all, no star is going to complete its main sequence lifetime, or its evolution from a red giant, quickly enough to let us here on Earth observe these structural changes as they happen. So instead of observing the evolution of a single solitary star, we can instead look at a group or a cluster of stars. And when we do this, we can assume that the stars in that group were all formed at nearly the same time from the same original interstellar cloud and therefore have the same composition. We expect that these stars will therefore differ only in mass, and their masses therefore determine how quickly they go through each stage of their lives. Since stars with higher masses evolve more quickly, we can find clusters in which massive stars have already completed their main sequence phase of evolution and become red giants, while stars of lower mass in this same cluster are still in the main sequence or undergoing the pre-main sequence gravitational contraction. The nice thing about this is we can see many stages of evolution among the members in a single cluster. And we can see whether our models really explain why the HI diagrams of clusters of different ages look the way they do. So let's talk about the first type of cluster we can observe, which is a globular cluster. So globular clusters are given this name because they are nearly symmetrical round systems of typically hundreds of thousands of stars. Now, the most massive globular cluster in our own galaxy is Omega Centauri, which is about 16,000 light years away and contains several million stars. Now, the brightest stars in this cluster, which are red giants that will complete the main sequence phase of their evolution, are going to be kind of a red-orange in color. Now, when we look at these stars, we also see they typically have a surface temperature of around 4,000 Kelvin. So this tracks a lot with what we know from our HR diagram. And so when we take a look at the Omega Centauri, we can start seeing, of course, a visual representation here in image A, and image B is going to kind of give us much more zoomed in one. And just looking at image A, we can see that we have several million stars here. So there's a lot of stars kind of packed into one small space. Now, the most numerous stars in this image, if we look at image B, which again is more zoomed in on the core, we can see that most of these stars are kind of a yellow-white in color, and therefore our main sequence stars, much like we would see our own sun. Now, the brightest stars, of course, in here are the red giants, and these, of course, have begun to exhaust their hydrogen and fuel and have expanded about 100 times the diameter of our own sun. In addition, we see some blue stars in here, which are stars, of course, have just started helium fusion. So, what would it be like if we could actually live inside of a globular cluster? Well, in these dense central regions, such as image B we just looked at, we would see that the stars would be roughly 1,000,000 times closer than that we see within our own local neighborhood. If Earth orbited actually one of these inner stars in a globular cluster, the nearest stars to us would be light months and not light years away. It would be pretty convenient if we were trying to travel to another one. These stars, of course, would still appear as points of light, but they would be brighter than any of the stars that we see kind of in our own night sky. In fact, they would be so bright that the Milky Way would actually be very difficult to see through the bright haze of starlight that is actually produced by the cluster. Now, there are about 150 globular clusters known within our own galaxy. Most of them are in a kind of spherical halo or cloud that surrounds the flat disk formed by the majority of our galaxy stars. Now, of the globular clusters that are very far away from the sun, we find, of course, some distances all the way up to 60,000 light years or more from the main disk of the Milky Way. Now, the diameters of globular star clusters range anywhere from about 50 light years to more than 450 light years. So we do have quite a size variety here. The next type of thing to discuss are open clusters. So these are a little bit different. Open clusters we tend to be finding in the disk of the galaxy and have a range of ages. Some are as old as or even older than that of our own sun. Now, the youngest open clusters are still tend to be associated with the interstellar matter from which they formed. Now, open clusters are smaller than globular clusters, usually only having diameters about 30 light years. So a lot different from like the large range that we were able to see before. And these typically only contain several dozen to several hundred stars versus like the millions that we saw with the Omega Centauri. Now, the stars in open clusters usually appear well separated from one another, even in the central regions, which explains why we tend to refer to these as open clusters. Now, our galaxy contains thousands of open clusters compared to like the 150 globular we saw. But we can only see a small fraction of these clusters. And the reason for this is interstellar dust, which is much more concentrated in the disk and therefore is going to dim the light of distant clusters so much that they end up becoming undetectable. Now, although the individual stars in an open cluster can survive for billions of years, the typical open cluster remains together as a cluster only for about 1,000,000 years, or at most several 100,000,000 years. Now, there's a couple reasons for this. First off, the average speed of the member stars within the cluster may be higher than the cluster's escape velocity, and the stars will gradually kind of evaporate or move away from that cluster. Now, close encounters of member stars within that cluster may also increase the velocity of one of its members to go beyond that escape velocity. And every few 100,000,000 years or so, the cluster may have a close encounter with a giant molecular cloud, and the gravitational force exerted by that cloud may actually tear the cluster apart. Now, the last thing that we need to talk about is stellar associations. Now, association is a group of extremely young stars, typically containing 5 to 50 hot, bright O and B stars that are scattered over regions of space, some 100 to 500 light years in diameter. For example, most of the stars in the constellation Orion form one of the nearest stellar associations. Now, associations also contain hundreds to thousands of low-mass stars, but these are much fainter and less conspicuous. But the presence of hot luminous stars does indicate that star formation and association has occurred within the last 1,000,000 years or so. Since O stars go through their entire lives in only about 1,000,000 years, they would not still be around unless star formation has occurred recently. It is therefore not surprising that associations are found in regions that are rich in gas and dust required to form new stars. On the other hand, because associations, like ordinary open clusters, lie in regions occupied by the dusty interstellar matter, many of these associations are actually hidden from our view here on Earth.